We're taking a look at sections 14.2 and 14.4. Okay, together though. Obviously, we're skipping 14.3. So when we start tomorrow, we're going to pick up with chapter 15 actually. Okay, so we're looking at chapter 14, which is the topic of light, but we're not doing 14.3. 14.3 has to do with curved mirrors that could be convex or concave. We're going to talk about them in general, so we are going to. But there's a lot of problems where you have to find the magnification of the image, which is not. First of all, a lot of it's not on your SAT physics. And second of all, a lot of it is work that if you want to be like an eye doctor, it's probably really useful. Or if you want to be, I don't know, someone that might be working on like, say again? Yeah, eye doctor, yeah. But I'm trying to think of another profession that would be using like lenses a lot. Okay, maybe somebody that like has to use a something to cut diamonds or like to look really close with. They need different magnifications of lenses. Okay? But generally speaking, the idea to know how it works is not as important as to be able to use it. So, for example, if you know how like a microscope works, or you can use a microscope rather, you need to know how magnification works on it, but it's not as necessary to know how the light rays get reflected and get refracted through the lens. So what I'm going to try and do is give you guys an overview with 14.2 and 14.4. Okay? So, we're going to look at 5 things today. First, we're going to talk about the difference between specular and diffuse reflection. We're going to discuss the law of reflection. We're going to recognize what are called additive colors. Additive colors, which we're going to call today as the primary colors. We're going to talk about how pigments affect the color of the reflected light, and the idea of polarization and what polarization is. Okay? So let's start with the first. First, we're going to talk about reflection. And this is my own definition. Your book doesn't give you one. Okay, or it gives you one, but it's a little bit odd, I think. I forget. But I wrote, when an electromagnetic wave is redirected outwardly at the surface of a material. Okay? So reflection is just some sort of EM wave. It doesn't have to be a light wave. So you might see your reflection in this glass right here. Because you can see, because it's a smooth surface. But when the light comes from the sky and hits the cement on a sunny day, part of that light gets reflected. And that's when sometimes you'll see like a glare, and that's when the light becomes polarized actually, when you see that glare. But for the most part, there is reflection occurring from every different surface, okay? Alright. Okay. So, if you have a surface that's rough, we're going to say that the light reflects off of it in a diffuse manner. And that's the image on the left. So what you're seeing is with a rough surface, and rough is a relative term. Rough means relative to the waves themselves. So these wavelengths, you can see how rough this is. And what's happening is they're hitting these little valleys and these peaks, which cause it to go off at different angles. Okay? So you're seeing this light wave come off at different angles. Whereas here, with a specular example of reflection, it's a smooth surface, and look at all the light waves that are reflecting off the surface. They're coming off in what direction to each other? What's the word? Not perpendicular. The other one. Parallel. These waves, and I'll draw what I'm talking about. These waves are all parallel to one another. Okay? The other waves could be perpendicular, but we don't know that, Paul. That's why I said no. Paul, this could be a 90-degree angle right here. If this is 45 and this is 45, that is definitely possible. So again, what Paul was talking about was this angle measuring between the incoming ray and the outgoing ray. Okay? Which we'll call the incident and the reflected. We'll talk. But again, the rays coming off...
They're just simply congruent, not
parallel. Congruent is different. Congruent has to do with length. These 4 waves coming off are all parallel to each other. Okay? So again, we're talking about these 4 waves coming off the reflection are all parallel. Okay? So that's why we say that they're reflected in one direction. Whereas these ones over here, this one is upward at almost a 90-degree angle. This one's at like a 30-degree angle. This is at like a 60. This is at like a 45. Those are all coming off at different angles. So when you have a diffuse reflection, it comes from a rough surface. Okay? When you have a smooth surface, you get specular reflection, which is something that you can see your own reflection in. So, the glass of a windshield, or the car door, or an actual mirror itself. Okay, there's many ways you can see your own reflection, and that has to do with specular reflection. Okay? You're never going to see your own reflection in something that's diffuse. It's got to be specular. It's got to be smooth.
What about water? Water.
Water is smooth. Even if it's got ripples, it still is smooth on the surface, right? Think about like, if you look at the concrete, like the black cement on the ground, you're not going to see your face in a reflection there. If there's water on it though, but it's not smooth actually. All those little crevices are make it really not smooth. So something like this tile floor, if it were waxed and shined so it was super smooth, you could actually see your reflection in it there with enough light. Right now you can't. The floor has scuff marks on it and it's not as... You can still see what?
By the blue.
Yeah. Oh, maybe...
I can see it on
Oh,
the
yeah, you can kind of
elements.
see a little bit, that's true.
Yeah.
And you can also see the reflection of the light. You can see the colors or the different white bands, right? And we're going to talk about that as interference. You can see certain bands at certain times.
Wait, how is this physics?
We're looking at the EM spectrum. So when we're talking about the electromagnetic spectrum, it's like radio waves, microwaves, visible spectrum. So we're specifically talking about, light now, and then we're going to talk about... No, that's not a problem at all. We're going to kind of mix in a little biology today also. Okay, so you'll see where that comes into play. Let's take a look at the second thing. The second thing is the idea of the law of reflection. And it's quite simple. The law of reflection simply says that the angle coming in is the same as the angle going out. So the angle of incidence, which is this theta right here, and I'll draw an arrow to it. The angle of incidence, which is the angle between the perpendicular, which we call the normal, and the actual ray itself, is called the angle of incidence. And that is equal to the angle of reflection, which is the angle coming off. Again, in the past...
Does that depend on whether it's specular or...
This is assuming a smooth surface. Very good, yes. That's very true.
Theta?
Okay? So let's make a point Garrett just said. This is for smooth surfaces. So assuming specular, yes. I knew I put that in there somewhere. For smooth surfaces, Garrett said. Okay? It's got to be specular. So it's theta and then theta prime. Just means like a second theta. Theta 1 and theta 2. Okay? No different. Now, what I do want to point out though is this. We always measured theta above the horizontal in physics, if you've noticed this year. When there's a projectile that's launched at an angle, haven't we always called this theta? Okay, we've always called this angle here theta. But now, for light rays, we're going to talk about the angle between the actual ray and the normal. Okay, which is like the vertical. Okay, the vertical. So the angles we're measuring now are no longer with the horizontal, but they're measured with the vertical. So make sure you write a little note here. Okay? Correct, and that would be 90 minus theta, and this would be 90 minus theta prime, because the angles are complementary. Okay? So again, as Fernando said, this is 90 minus theta prime, and this is 90 minus theta. Those are also the same. So you can measure these angles instead. It really doesn't matter. Okay, but when your book refers to angle of incidence and angle of reflection, you're going to see it drawn with respect to the vertical or the normal. Okay, so we're going to be talking about these angles in here. Okay, that's what the book is going to be talking about.
What's that? That's the theta 1, right?
So theta prime, it's like an apostrophe. Okay, so just in math, a prime just means like a second angle instead of theta 1 and 2. Like a second angle.
Oh,
so like theta is just an angle coming in. Theta prime is the angle that's been altered, even though it's the same. Next.
Tell us like which theta is which.
Yeah, this is not. There's not much you can do with this besides for now know that the angle coming in is the angle going out. Okay, and know the terminology. Angle of incidence. Okay, incidence and angle of reflection. We're going to talk about Snell's law later on, which has to do with light rays that pass through the surface. If it's like glass, and those light rays get refracted and changed. So these angles coming in are going to be very important. You're not going to see any mathematical application in this section, but when we get to chapter 15, which we're going to really start tomorrow, we're going to see more about that and how that actually plays a role. Okay? So again, angle coming in is the same as the angle being reflected. All right, let's look at the next thing. We're going to look at the visible spectrum and get an idea. This is now section 14.4. Okay, that first two slides is all we're doing from 14.2. Okay, so this is section 14.4 now. So the visible spectrum, remember obviously Roy G. Biv, which all of you I think know already, but I just wrote it in case anybody doesn't know the acronym. Okay, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And I think about green as splitting it down the middle, right? Red, orange, yellow, aren't those like the colors of a fire? Right? They all go together, red, orange, yellow. And then blue, indigo, violet also go together here. Blue, indigo, violet. And then the green,
There's two greens.
the green red.
No, it goes red, orange, yellow. Green.
Oh, they don't put indigo on here. That's interesting. See that? ROYGBV. Okay, there's no indigo there for some reason. I never seen that. Anyhow, think about green as the light ray that's splitting them up. Now, this is what we want to talk about. The definition of what color really is. Okay? And color is the result of a surface that absorbs only parts of the visible spectrum and reflects only one. Okay, it absorbs parts of the visible spectrum and reflects only one of them. So this leaf right here that you see every day outside on the tree that's green, what you're seeing is the fact that that leaf absorbs every color except for green. That's all that's happening here. Again, every color is accepted into the leaf or absorbed by the leaf except for green. Green is reflected off the surface, so that's why you see green. Your shirt, Garrett, is white and blue. The blue you're seeing just means that blue is being reflected. What is the white color, though? You know what that is,
It
Garrett?
absorbs all of it. No, I'm just kidding. Reflects all. Reflects all.
Reflects all.
Oh, I knew it was
Okay.
one.
Oh, wait.
It's
So
black
write a little
and
side
blue.
note. White, when you see the color white on your notebook, you're going to see white, you're going to see it's a reflection of all colors. That's why in the summertime, you're told wear a white t-shirt. Why do you wear a white t-shirt like to the beach or something? So you don't get heated up. So it reflects all the light. Now, why do you not wear a black t-shirt in the summer for the opposite?
You get hot.
Okay? What happens when you see a black color?
Oh, it absorbs all the.
It absorbs all the rays of the spectrum.
That's why pavement is
Okay.
really hot.
And that's exactly right. If you ever look at blacktop, listen guys. If you ever look at blacktop, like a basketball court, or like say a street is paved over with asphalt, which is a black color, you're going to see that it's actually very hot in the summer. When I was a kid, I grew up and my dad built us a basketball court in the backyard when we were young, and it was asphalt, so it was just like black concrete. And every summer we would complain, even though like we loved playing basketball, but certain days you couldn't go out there and play because we'd like to play barefoot, and you couldn't walk on there barefoot. You have to wear sneakers. So what we ended up doing was coating it with something that actually reflected some of the light. It gave it a bit of a glare, but it actually helped it. I mean, it's the same thing as putting water on the surface. The water cools it off, but the water will also reflect some of the light. Okay, so it'll cool it off in two ways: by actual convection on the actual surface of the water.
Won't it magnify the heat?
No, it doesn't actually, because the water actually reflects more of it. Some of it will get angled and changed, but it's not going to magnify it. It's going to reflect it.
My
Livia,
friend,
Livia.
was that video
Pleasure.
you posted on the, was it the forum where it's like, yellow is every color except for yellow?
Yep.
Something like that.
So green is every color being absorbed except for green. Blue is every color being absorbed into that object except for blue. So when you see things don't really have inherent colors, they have pigments. And the pigments denote what they're going to accept as a color. So this door probably accepts a bunch of different pigments because it's showing off as brown. Brown is not one of our colors. Brown is a combination of red, orange, and yellow, actually. That's what you're seeing. So you can have tints, and that's where tints come into play.
Yeah, my friend lives in Florida, and he was playing like tennis. He like played it all day, and at the end of the day, he took his shoes off and like was looking at them, and at the bottom they were like they were like pretty new, so like the tread was there, but then at the end of the day, the tread was completely like melted away.
Because it was so hot and pavement.
Yeah, it was
Yeah?
so hot. It was
That makes sense. That makes sense.
And I was
The other thing I was thinking about was the fact that lost my train of thought there.
Yellow.
I know, that's my point.
Tints, thank you. Okay. So, very good. Another application of this we're going to talk about in a second are the primary colors. They're going to come into play when we think about our eyes and we think about TVs. Those are the two most common things. Okay? And you've seen this before, this symbol. Okay? This is just your simple what?
Colors.
Like a color wheel almost. Okay? Who's in art here? Who takes art?
Oh yeah,
Okay. What is this actually called? Is there a term for it? This image? Color wheel?
I got it.
Primary color wheel?
Yeah.
The primary colors are green, red, and blue.
No.
Yellow.
Green is yellow and blue together.
Because
Yellow.
yellow is green and blue.
Sorry, you guys are. It's not green.
Guys, the three primary colors that you see are these three colors right here.
It's not
Green,
yellow.
red, and blue.
Yellow.
It's not yellow, guys.
It's
You,
definitely.
go ahead. I'm not lying to you guys.
Green is yellow.
Anyway, guys, just listen to me.
Three primary colors.
Listen. Yellow is the combination of green and red. Garrett, look up so you can see what I'm talking about. This combination, the overlying, is yellow.
No, but there are three primary colors. Like this. Okay. Wait.
But orange and
No,
red.
yellow is
and
created from blue and green.
Search those.
Okay, I'm just telling you in physics, these are the three colors that we look at as the three additive primary colors. Maybe in art it's different. Okay? But I'm not lying to you guys, I promise. Now, next. Well, you'll notice when you look at a TV, you're also going to see that they have three colors. And your eyes have receptors in them called cones that can receive three colors. And what you see is the combination of those three colors. So depending on the brightness or the intensity of them, you're going to see different ones for each of them.
Wait, it even says green.
Okay. So,
No,
in art it's different, guys. In art it's different.
I know, but it even says green there.
Yeah, and that's what I'm saying. But he's saying in art they learn that is yellow. What is it in art?
Yellow, red, blue.
Yellow, red, and blue in art. Okay, but this is always the way I've learned it. This is the way I taught primary colors. Anyway, what I'm getting at is this: in a TV, when you look at your TV, you're seeing pixels, right? What's a pixel? Who can describe what a pixel actually is?
It's like it's sort of like one tiny like bulb that like does light.
That's exactly right. It's one tiny, almost infinitesimally small bulb that gives us a little bit of light. Okay, focus, gentlemen.
No, he's got like
The note taker.
Yeah.
Now, what you're going to notice is with a TV, you only have those three colors. You only have those three colors. Okay, we're all standing there. Let's look up here, please. Jack, you too. Thank you. Up here? Like, look up here, please. Thanks. So, we're only seeing those three colors in the TV. That's all you're seeing. And when you look, if you go to your menu and look at your color scheme, you'll see that there's a balance. And you'll see a balance between these colors. Okay, and it'll give you you can go to 50% or beyond 50%. You can go up to 100% of each color, and it'll change what the screen actually looks like. So a person that, say again?
You can make your full screen red.
Yeah, you can make a lot more of it red. You can change the intensity of each of the colors. And what will happen is over time, TVs will, some of the bulbs will go out, or some of the intensity or the brightnesses will change. So what you'll notice for each of them is that, focus, Karen, come on. What you'll notice for each of them is that if you change those intensities or those numbers, you're going to see a difference on the actual screen.
It's the more pixels, the better.
Yeah. The more pixels, the more precise of a picture you're going to have. So when you see 1080p, it has to do with the pixel measurement. When you look at 720p, what does that mean?
Oh,
No, 1080p is more.
1080 is more, and 720 is fewer.
Yeah.
So what you're seeing each time is there's going to be less of a resolution. Very good.
Yeah, less
Okay? There's a lot more that goes into TVs than just that. But you can see the three. Now, in biology, who remembers what the things were called in your eyes that receive colors? What are they? Your cones. And in human eyes, you have three different cones. You have the blue receptor, you have the red receptor, you have the green receptor, those three cones. Now, based on those three cones, stop it, gentlemen. Based on those three cones, you can see different colors. I see him waving, I see him standing out there.
let's say bye.
Okay.
Okay.
So, what we're noticing here is that the three different cones receive different tints.
Never miss a mom.
If you see something that might be orange, you're seeing a combination or almost a blend of those two cones that are receiving different colors. Okay? I don't know. What are the cones versus rods? Rods receive what kind of a black and white? Okay. So dark. All right, last thing. Last thing for today, polarization. Okay, polarization. Polarization is going to take us a little while to talk about. You do not need to draw those images, and I don't really recommend you do. It's going to look very confusing. And it's tough to see because the yellow, I don't know why the book chooses to use yellow waves. There's actually yellow waves here. You can barely see them. But there's yellow waves on here. And there's yellow waves on top of yellow. Okay? You need to refrain yourself from that stuff. Come on. So I'm going to cover those yellow waves in green so you can see a little bit better. Okay, so I covered them in green. But you'll notice, for each of these, first of all, definition of polarization. The alignment of the EM wave, or of EM waves, in such a way that the vibrations of the electric fields are parallel to one another. So the first image you're seeing at the top is unpolarized. And take a look at the green waves that I've outlined. Those are the EM fields, the electric fields here. The electric fields are not parallel to one another. This one is coming out of the page here, and this is going into the page. This is coming out of the page at a different angle. This one is just perfectly up and down. And then if you look down here, you'll see those waves are all parallel to one another. They're identical. So all that's happening here is the electric fields are changing their angle. That's what polarization is. So what you'll notice in the summer, or just in general, sometimes there'll be like a slick surface, like there'll be water on pavement, and you'll see a glare. And you can see that glare from a good distance. You're seeing light that has almost, or has reflected off of the surface, but it's come off polarized. That's why you're seeing a glare. The light itself is polarized. So when you buy glasses and they say, you want to get those glasses polarized? What's happening really is this. They're putting some sort of a material or a layer of film on the glasses that is able to depolarize the light and the glare. That's what's actually happening. So two polarizations cancel each other out.
Like polarized
So you're seeing polarized sunglasses. So you're seeing this. That happened about 30 seconds ago.
Like polar bears.
It did.
He said glasses though.
No.
It's the same thing though. Yeah.
Yeah, but
sunglasses
sunglasses are more common where you're like.
Absolutely. No, he's absolutely right. Sunglasses are a lot more common.
What about ski goggles?
Really dark shade, so it like kind of just did it by itself. But you see sunglasses that look very light, and they still are.
And they still are,
These
yeah.
are polarized. And you wouldn't.
Yep.
You wouldn't
My regular glasses that are transparent, they don't have any tinting, are
What
polarized.
does that do though?
So Jeff, that's a good point you make, because a lot of people think that polarized means it's a darker color of the actual shade, which keeps like the light outside dark. That's not what happens. What polarized sunglasses do, okay, is polarized sunglasses are able to trap the polarized waves or reflect the polarized waves so they don't pass through the glasses. So what you're seeing there is the fact that you get these waves that come off as a glare, or you get a glare off the surface, and your polarized glasses are able to take those waves that come off as a glare that are polarized and reflect them back so they don't come through the glasses. So if you ever have glasses that you wear for driving, I know for me at night, I have to wear my glasses for driving, always. Because I have trouble seeing at night when I drive. And it's a lot more difficult, people notice. If you have, my vision is not even bad. It's like 45-20, which is really barely even needed for like glasses at all. So during the day, I don't even wear my glasses. But at night, if I ever drive, I have to wear them. And what else I got was I got the polarized ones because you get a lot of glare at night in cars. The headlights, there's glare from them. So what the glasses do that are polarized at night is they also reduce that glare. So it helps you see better at night when you're driving. So when they tell you, like, do you want to get it polarized, it actually does work. It's not like a scheme to make more money off of you. It actually is useful to have. Okay? Max, you had your hand up.
Oh yeah, they have like
Shoot.
they have like night glasses for driving.
Yep.
My mom got some.
And did she actually, not night vision goggles, did she actually notice a difference though? What did you ask her, or do you even know? Did she mention it ever?
I've used them twice now.
Okay. All right. Well, that's unfortunate. Yeah.
There's these infrared glasses for dogs now. Maybe we were talking about that in here.
Infrared glasses. We were talking about that here.
Yeah. For dogs.
With the military?
Yeah.
Yeah, when they captured Bin Laden, that's what we were talking about. Oh, that's cool. That's all right. He probably thought he heard it somewhere else. That's fine.
Dude,
I forget that too. Let's see. That's pretty much it for this section, guys. That's it for section 14.2 and 14.4. Okay, your homework section is only one problem, and then I want you to read 3 pages. Okay, your homework is just to work on this one problem, and then read 3 different pages. We've got about 4 or 5 minutes, a little bit more. It looks like 5 or 6 minutes. Okay?
Wait, can I tell you? Can you still?
Yeah, I'm going to go over your test grades with you, yeah.
Can you still give us time to do the extra credit? Because I've been still busy with new
Well, what?
essays.